The gradient vector part 2. In this video, I want to go over two important applications of the gradient and to do an example for each one. My first theorem, suppose that f is a differentiable function of more than one variable. Here I'm assuming of x and y, but it can be of more variables. Then the maximum value of the directional derivative in the direction of the unit vector u is the magnitude of the gradient vector. And this occurs when the unit vector has the same direction as the gradient itself. The proof is pretty straightforward. We saw that the directional derivative of f in the direction of u was given by the gradient of f dot product with the unit vector. Now we know that to be the magnitude of the gradient vector times the magnitude of u times the cosine of theta. Well, the magnitude of u is 1 because it's a unit vector. So when is this the greatest? This is a maximum when the cosine of theta equals 1. That's the greatest value for cosine, which means when the angle is 0. So notice that the maximum value occurs and is the gradient times 1, or simply the gradient. This is the proof for the first part. And occurs when u, that is when theta, is the same direction as the gradient. Well, if I have two vectors and the angle between them is 0, then they're going in the same direction. So for this example, let f of xy equal x times e to the y. Find the direction of the maximum rate of change as well as the maximum rate of change at the point xy equals 2, 0. Anytime I'm doing a maximum rate of change, when I'm dealing with f of xy at a point, I want to find the gradient first. So the gradient, being the vector of partial derivatives, is going to be e to the y, comma, x e to the y. Now we're at the point 2, 0, xy equals 2, 0. So that's going to give the gradient to be e to the 0, and then 2 times e to the 0, or 1, 2. So this is the direction of maximum change, or the direction of the maximum rate of change. And then the maximum rate of change itself which I'll just call the max rate of change, is going to be the magnitude of the gradient at that point, or the square root of 1 squared plus 2 squared, which equals the square root of 5. So the first application, just to go back and revisit, which has two parts, is that at any point, the gradient is going to give the direction of the maximum rate of change, and then the magnitude of the gradient will give the actual maximum rate of change. Let's consider a different application. Suppose I have a surface in space and there's a level curve. So recall that a level curve is a curve on the surface at a fixed or constant height z. So something like this. So if I was traveling around this mountain, I like to consider my surfaces as mountains, that path would always be at the same altitude or at the same z value above the xy plane. In other words, I have a level curve, f of xy equals some constant k. Now, suppose that c, this curve over here, is parameterized or described as r of t equals x of t comma y of t. And let's simply find the derivative of f of xy, or the derivative of z, with respect to t. From our chain rule, we get that this is the partial of z with respect to x times dx dt plus the partial of z with respect to y times dy dt. That's simply from the chain rule. But since this equals a constant, I know I could set this equal to 0. Now, rewriting or changing notation, notice that I can write this as the partial of f with respect to x times x prime of t plus the partial of f with respect to y times y prime of t, which turns out to be what? Well, the dot product of fx comma fy with x prime comma y prime, or the dot product of the gradient with r prime of t. And once again, this equals 0, because I have a level curve in this case. What does that tell me? Well, that implies, and I'm going to draw a representative r prime up here. So r is the curve and r prime is tangent to the curve. What that implies is that the gradient must be perpendicular to r prime. Because when the dot product is 0, the two vectors are perpendicular or orthogonal. More generally, suppose that S is a surface with the equation f of x, y, z equals k. K is a constant. That is, S is a level surface of f. So it's a level surface of a four-dimensional thing, but I'm taking a constant view or a constant surface of that. Now, consider C, which is going to be a curve on my level surface, and I'm going to let C equal r of t. So C is on S, and it's going to pass through a point P. I'll call P x naught, y naught, z naught. If I were to do the derivative of big F with respect to t, that would be the partial of f with respect to x times dx dt plus the partial big F with respect to y times dy dt plus the partial big F with respect to z times dz dt. And because I have a level surface that f equals a constant, the derivative of the other side would be 0. And once again, just in higher dimensions, I see that I have the gradient of x, y, z, dot product with r prime of t, where we call that r of t will be parameterized as x of t, y of t, and z of t, and that equals 0. So my gradient is perpendicular to my level curve. Along those lines. So it seems like I just repeated what I did above, just as more variables, and I sort of did, but I want this for the following application. Suppose I want to find the equation of a tangent plane to x squared over 4 plus y squared plus z squared over 9 equals 3 at the point -2, 1, -3. How could I do this? Well, recall that the equation of a plane with a normal vector n equals ABC is given by a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. So I already have my x naught, y naught, z naught over here. The only thing I'm missing is my normal vector n. Well, how could I find a normal vector to my curve? Well, I could do that, of course, by doing the gradient of my curve. So the gradient would be the vector partial of this with respect to x, so 1/2 x, then the partial of that with respect to y, 2y, then the partial of that with respect to z, so 2/9z. And then the partials or the gradient at the point -2, 1, -3 will be given by 1/2 times -2, -1, 2 times 1, or 2, and then 2/9 times -3, or -2/3. So this is my normal vector ABC. And now I can simply plug in to get my equation. We get -1 times x minus -2 plus b, or 2, times y minus 1 plus c, or -2/3, times z minus -3 equals 0. And I will leave it at that. You can work it out if you like to, if you want to find the d value.